Okay, so yesterday we did another configuration of these coils, one or two different ones, and looked at the resonant frequency, and we're pretty much doing the same thing today, except what you'll see is that there's the addition of these potential coils here. And if you looked at the one of the last three videos that I released a couple days ago, where we go over the papers of the coil design, that this is not a primary and this is not a secondary. This entire combination of the current and potential coil is an extra coil, and that's an extra coil. So there's two extra coils, and there is going to be no primary or secondary in this system, and that's one of the unique features of this. And what we're going to do now is recheck what the resonant frequency is going to be with the potential coils added to the system. And with the potential coils facing out, this is more appropriate for like the flame speaker and shooting sparks.
Yeah.
And then for the cosmic induction generator demonstration, the potential coils will be facing in, and then the plasma bulb will go in the middle. And so it's kind of universal depending on what you want to accomplish. So we have the field strength meter over here. We're using the same BK Precision 401 4B digital signal generator, and I think it's on about 5 volts right now. And what frequency range are we going to start out at?
Well, let's start from 4 and work our way down.
Okay, so we're going to do 4 megahertz.
Well, actually 4.5. Let's start at 4.5.
4.5.
100 kc steps to start with.
Okay, the output is on, and what steps?
100 kc.
Okay, we're ready.
Okay, go full voltage.
Okay, let's see the amplitude.
It's 10 volts.
10, frequency.
Okay, now we
Okay,
have
so you can dial it for the hundreds if you
a
want.
little bit of a reading. It's glitched. Went something else. Got to go to
Oh, close. Okay, so
yeah.
let's put it back on.
4.5
range.
megacycles.
Let's turn it off, turn it back on. Amplitude 10, 4.5. Output's on 100. So it's set to go up and down in 100 kilocycle steps.
Something keeps jumping away on me. Okay, I see it because I'm going so wide. That's what it is. Okay, the resonance is kind of way too high. Boy, is this sharp.
So I'll zoom in on that meter.
Oh, because that's running 100 kc. Okay. Now let me see if I can find a lower. That's it. Well, it's kind of problematic because it's higher than it's supposed to be. Okay, let's go to 1 kc steps.
Okay.
That seems to be it. 0.7. It should be down around 3. Let's go to 10 kc step. Wait a minute, okay, well that's it. So we're way off. Now that's problematic. Yeah, there's nothing down there.
Puts on.
And it's on.
There it goes.
Turn the voltage down. And,
That's 9, 8.
keep going until there we
Okay,
go.
that's 3.
Yeah, but there.
So what do you want?
Right about there.
Okay. Back on frequency. 10 kilocycle steps.
Let's go to 1
1 volt.
kilocycle steps.
110. Okay.
Pretty sharp. Okay. 5, 6, 8, 8. Put these down. Well, it's kind of back to the drawing board.
Five 5.688 megacycle is where the frequency is at right now.
The calculator. Okay, the magnification factor is about 470. Okay.
So the upper and lower frequencies are where the meter is at about 70% of peak, and peak would be the center. And when you look at that span, that's the bandwidth. And the center frequency divided by that bandwidth is the multiplication factor. So 1 volt in is 470 volts out. So what's the next step since it's higher than?
It's kind of means it has to be all done all over again under different scaling. We'll have to think about it for a while. Why it would work out like that.
Okay, these were just turned 90 degrees and we're just going to measure it again just to see what happens.
Let's go back to tens.
It's about to start moving.
I know, but well, let's see. Still way up in the fives. Okay. That's just where they're going to operate at. The other things we can try to point them at each other, but I don't know if we have enough lead length here. Closer together. And it's still in 5. And that's about as heavy loading as you can get. Okay, well. I don't know why with the same amount of turns that I used before, why they're so higher. So basically, what was our original frequency? How much farther do we have to scale it? Seven roughly. Three. It's going to be 1.7 times bigger. Or more turns.
Mm-hmm. So we got to figure the most time effective way to do it, which may not be optimum, but we're getting to the point of so some extra turns on these.
Well, we have to have 1.7 times the turns.
1.7.
So if we use the same forms
Uh-huh.
and have 1.7 times the turns,
Uh-huh.
then that should work out. So actually, I think the way that we should have done this was rough wind them first and see. You know, the forms are still good. So we basically just need different windings on the forms with almost twice the wire. And I think it'd probably be best just to start it with some, regular wire first before trying to form these number 8 things. And if we need to, then... So that's what we're going to do. We're just going to use the same forms, and we have to change the number of turns.
And these need extra turns on this side too?
Yeah, both of them. It's going to be 1.7 times. So how many turns are there here? I think it was 30. Or... So I'd say
Well, that's if we can separate this from those with that chronodope on there without cracking.
Yeah.
Otherwise, if those have to be redone, we need to do something other than this glass rod, because it's...
Well, I think that corona dope breaks, if you tried to break it loose, I don't know.
Might.
No experience with it.
Yeah.
Well, the other thing is, you know, is to build one of these for 5.7 megacycles, but that's going to be,
Yeah, right.
you know?
5 point. So it's 25.5 turns on the big wire.
How many turns are on there now?
I think 15. I think it's 15 and 30.
Yeah.
So if it's 15, that's 25.5.
So we'll probably have to use number 10 wire to get enough winding on there.
And this is 8.
Yeah.
So that's 10.5 more turns. So 10, 2, 4, 6, 8, 10. Divided by that space. Yeah, because there's going to have to be, we'll see, how's it going to, because it's got to be sawed
Yeah.
for extra turns. But I don't think these can come apart now.
Well, no, we can't saw anything. No, we have to get,
So they'll just
we'll
have
have
to
to use
land.
smaller wire.
Yeah.
We have to use 10 or 12. Or like the other thing is build some kind of master oscillator that operates at that frequency. I mean, we got these tuning units here.
Uh-huh.
One of those will, could use one of those tuning units.
The master oscillator section.
Well, both sections. Once, well, we can put tubes and power supply to those things. That's one way to deal with it.
So basically just keep one unit intact.
Well, there's one that will operate.
For that band?
Yeah, they'll have to be, you know, they'll have to be the one that.
Okay, so this is basically just another test to verify the bandwidth and multiplication factor. And so we have these pointing outwards, which the small potential coils would be making the sparks outward, and you would turn them inwards if you want that, the potential coils aiming into a plasma bulb, for example, for like the cosmic induction generator. So we have this Simpson style voltmeter as the field strength meter. Positive is just sitting inside of a cup underneath one of the potential coils. We got the kind of the current transformer concept here, which is similar to what we showed at the conference on how to determine the resonant frequency of the multi-wave oscillators using this BK signal generator. And so what we have is, in the center frequency is 5.699 megacycle.
Kilocycles.
Well,
Kilocycles.
I did say point.
The point, okay.
Yeah.
But use kilocycles,
So,
not megacycles.
So 5699 kilocycles is the resonant frequency, and what we do is we control the amplitude of the voltage of the signal generator so that at the resonant frequency the needle is at 100%, which is right at the, you could say, the 10 spot. And so then what we do is we dial the frequency down, and I'm doing multiples of I think 100 at a time, and I'm going down, and so that means that the frequency is, or the needle is going to go down a little bit until we're at 7.07 times, roughly about 70% of the peak, and that's going to be the lower limit right there, which is 5694 kilocycles. And then what we do is we turn it up, and then what it's going to do is it's going to peak, and as we go past that frequency it's going to start dipping again because we're getting out of the resonant range, and we do that until it also drops down to 70%, or about, you know, more specifically 7.07. And the upper one is 5705 kilocycle, and so if we look at the upper and lower range and we subtract them, what we have is a bandwidth of 11 kilocycles, which is really tight. And it's the tighter the bandwidth, the more desirable that is, because there's more energy within there. It's more concentrated within a very narrow range. And then if we take the spread and we divide that by that bandwidth of 11 kilocycles, we have 518, and that's going to tell you the multiplication factor. So for every 1 volt going in, you're going to get 518 volts coming out. I don't know where that little, let's see. So what I'm going to do is I'm just going to, and we'll have this kind of at a distance sitting on this stool here, because it's so sensitive that, you know, 4 or 5 feet away, Eric's going to wave his hand there. You can see that this meter is moving back and forth, so it's detuning it. So it's very, very sensitive. I'm going to turn the dial back down because we went above the resonant frequency. And we're going to see that I'll zoom into the meter there. Right when I turn it down in frequency and we get right at the end of the scale, that's 100%. And what we can see is that we're at about 5.698, 5.699. You can see that's really close, and that's the resonant frequency, and that's why it's at the end of the scale. So it's in the resonant frequency right now. So that's what we've come up with. Now, also what we've come up with is the fact that this is operating at a frequency higher than what we hoped. The Collins unit goes up to 4 megacycle, and then it skips up to 6.4, and the range where these are operating at just happens to be in that missing area. And so what we're going to do is we have an alternate method. I mean, we could obviously rebuild the coils, but these are so time consuming. Whatever frequency these are operating at, we're going to build we're going to compensate for that by building something more specific.
We're going to build our own Collins, and this is going to be all the tuning will be here. This will be the master oscillator and the output.
So this is a TU7B tuning unit for that range.
Right.
And what is that saying?
We've already been using these, so
4,500 to 6,200 kilocycles.
Yeah, so this is our range, and this is the master oscillator. So this does the tuning and sets up the frequency. So we'll build an oscillator stage to connect on this, like the transmitter it came out of. What was it? A BC 375.
I believe so. I think it's on those papers.
Yeah, we're building a compact version of the BC 375, because this whole thing has to fit in the 10.5-inch panel space. So this is the master oscillator coil, and this is the power amplifier plate coil. We'll have to center tap it because we're going to make this push-pull to get lots of power in a small box, and then the rest of the 10.5 inches will hold all the vacuum tubes and their associated parasitic suppressors. And then the control panel and the rectifier panel will be out of this, so we can get it to fit in the space. And then this will do what the Collins does basically as far as power. 100 watts RF maximum output.
So it'll be this plus...
Yeah. Plus we have the master oscillator. This is what they call MOPA or MOPA, something that's been horribly distorted in its use by liars and fools. So normally you have a separate oscillator that's stabilized, and then you let that generate the frequency, and then you start adding the power, where in a self-oscillating system it's the power amplifier itself that oscillates. And that's why nobody's getting anywhere with these Tesla transformers, is they just let them self-oscillate. This one's not going to be a self-oscillating one. This one's going to have a master oscillator.
So basically the power supply amp is the unit that's going to go with this.
The power supply will be in the power control panel, that one marked out on the bottom there. So that will provide the necessary DC power. And then the Collins went in here. So everything that does has got to fit in this space, and then this panel, which is the same as this panel, the grid control panel, that will have the controls for measuring the tube current and all that kind of stuff in the RF unit. So it'll all fit together really good. So the only complication is getting backup from this impedance to the impedance to drive the grids of the power tubes. It's not really going to work out the way that I had it originally planned, so that's the part that goes in here that replaces this that has the big tubes. So that's still in the future. So it seems like it'll all fit together. It's going to be tight. As it's always been. It's always 5 pounds in a 10-pound bag. No, 10 pounds in a 5-pound bag.
But it should be considerably lighter than this Collins, which this thing is
dedicated
massive.
to what actually is going on rather than being something that was adapted to it. Plus, this thing is a waste. It has all these ham radio capabilities. They use this just as a one-frequency exciter, as kind of... it's a waste when you can get on the ham bands with that thing on any of the frequencies.
Okay, so
might need more light until it gets going.
Let's see.
I got to any motion in here. The problem is I can't move. Put the meter over here. I can see it. Yeah.
So what we're doing is we're just going to tune it for its resonance while Eric is bringing the tube up to it, because just by bringing your hand towards it will detune the system. So that obviously means that when you have the tube up there, you tune it to be in resonance with all that coupling.
It doesn't seem to want to start now. There we go.
There it's on.
Ignited. There we go. Okay, we got a free space now. Almost. Just this little 100 milliwatt.
And so that's 10 volts out the signal generator with hardly any current, and it's amplifying the voltage enough to at least light this little tube.
Yeah.
And it is not metallically connected.
That's pretty good. It's pretty good power conversion. Everything that's coming out of the oscillator is going into the fluorescent lamp with no losses. So this thing's doing its job. If this little peewee oscillator can get the tube to light up that bright, this thing's working.
Yeah.
Because that's not a lot of energy.
Flea power.
Yeah. Well, I'm satisfied. This thing's cranking. Okay, if I take it away, the whole thing will snap out. So do you have enough? Okay.